Okay, for this question is similar to a database question. You are to suggest which is the better container for cooling down drinks, and we must know that the better container is one that allows you to cool down the drink faster. So you want to put the container of drink inside the fridge, and you want it to cool it down very fast. You don't want to wait, very long for the drink to be cooled down, right? So let's calculate out the amount of energy needed uh, to be extracted from the container before it can cool down. So using the specific capacity equation, so if you write it in this way, it's Q equals to MC change in temperature. You realize that for the aluminum can and the glass bottle, the aluminum can actually uses, or rather requires lesser energy to be extracted out for it to cool down by 1 degree Celsius. For the glass bottle, for it to cool down by the same amount of uh, temperature, 1 degree Celsius, you need to extract out a lot more energy, probably because of the glass bottle having a bigger mass. So the aluminum can will be a better container to store your drink and for it to cool down because it'll be faster. The refrigerator wouldn't need to work so hard and work for so long to extract out the energy from the aluminum can. After all, the fridge only needs to pull out 22.5 joules of energy from the aluminum can before it can cool it down by 1 degree Celsius. Whereas for the glass bottle, um, only when the fridge draws out 150 joules of thermal energy from the glass bottle, then the glass bottle will cool down by 1 degree Celsius. It's going to take a long uh, time. In fact, I think roughly 5 times longer to cool down the glass bottle. Now, in part B, you are to calculate the final temperature when you add milk to the coffee. So, for this kind of question, the final temperature, just let it be T1. Just use algebra to solve this. And this is an important equation to note. Essentially, always identify what is the hotter object because the hotter object will cool down and lose the thermal energy. This thermal energy will then be given to the, the cooler object. So in this case, the coffee is the hotter object. The energy loss and the energy loss will be gained by the cooler object, which is the milk, to heat it up. Plug in the equation on both sides. The same equation that we used just now can be used here. And take note of the change in temperature. Okay, as the coffee is hotter, so the change in temperature is from 85 dropping to a smaller value of T, and the milk was cooler, so uh, the milk would have heated up. So the final temperature T will be a higher temperature. So T minus away 5 degrees Celsius. Uh, Therefore, with this calculation, you'll be able to get T1 equals to 70.1 degrees Celsius. Part 2 is a very difficult question, but we can solve this together. Okay, so in this case, you have three things to consider. You have the coffee, you have the milk inside. The milk is inside already, and lastly, you have a copper teaspoon. All right, there's a cup outside, but let's just ignore it for now. Okay, so you have to factor in these three objects and then determine what is the final temperature of of everything of the chister, is it? So the answer here is 68.7 degrees Celsius. Again, the strategy to solving this is the same as previous. Let the final temperature of everything, which is the coffee and the milk. Always remember the milk is inside already. Okay, let the final temperature be T2. So the energy lost by the hotter object. In this case, the hotter object is the combination of a coffee and milk. This energy loss by the hotter object will be gained by the cooler object. Okay, the cooler object will then uh, increase temperature. The hotter object will then decrease its temperature. Alright, so the first term over here is the coffee. The coffee was at 70.1 degrees Celsius from your answer in part 1. It was hot, but because you put in the teaspoon that is cooler, this will cool down the hot coffee by a bit. So the final temperature is T2, so we use 70.1 minus T2 to find the change in temperature. Now, the second bracket over here is about the milk. Alright, the milk is also at a very hot temperature, 70.1 degrees Celsius, and it gets cooled down to the final temperature of T2, which is lesser than 70.1. Then finally, the energy gained by the originally very cold teaspoon. The teaspoon was at 20 degrees Celsius, very cold, and when you put it inside the hot coffee and milk, the teaspoon will then heat up to a final temperature of T2. That's why the change in temperature is T2 minus 20 degrees Celsius. So if you put all this into an equation, you can calculate out what is the final temperature of everything, which is 68.7 degrees Celsius. For those who make your own coffee or Milo for the matter, this will be quite obvious. Alright, so I don't add sugar to my coffee, but if I were to add sugar to my coffee or Milo, I will definitely add it first before I add the milk. The reason is very simple, really. The coffee is very hot, so you want to add in the sugar first when the coffee is very hot so that it can dissolve faster. Now, if you add in the cold milk first, the cold milk will decrease the temperature of the coffee and your mixture will be of a lower temperature. Then when you add in the sugar, it will become a bit more difficult for you to dissolve the sugar. So always add in the milk the last, because that will decrease the temperature of your drink.